In example 6, they've asked us to determine whether g of x equals sine 2x plus 2x satisfies the hypothesis of the mean value theorem on the interval from 0 to pi. So sine 2x plus 2x is both continuous and differentiable. It's continuous over all real numbers. It's continuous over the closed interval from 0 to pi, and it's certainly differentiable over the open interval from 0 to pi. So it does satisfy the hypotheses of the mean value theorem. So let's see if we can find these values c in the open interval 0 pi such that the mean value theorem would be satisfied. So first of all, let's take a look at this function g of x. So g of x is equal to sine 2x plus 2x. And if we differentiate this, we get g prime of x is equal to the derivative of sine is cosine of 2x. Now, applying the chain rule, we differentiate 2x, and the derivative of 2x is 2, so that comes out front. And the derivative of 2x, again, is 2. So there we have our first derivative. Now, this is just a rearranging of the average rate of change equal to the instantaneous rate of change. They just multiplied through by b minus a. And, you can use either representation of the mean value theorem, but, since they've written it like this, we'll use it like this. So it's going to be g of pi minus g of 0 is equal to g prime of c times pi minus 0. Okay, so what is g of pi? Well, let's figure this out. So g of pi is equal to sine of 2 pi plus 2 pi. Well, sine of 2 pi is 0, and so this is just going to be equal to 2 pi. Now, let's see what g of 0 is. So g of 0 is equal to sine of 2 times 0 plus 2 times 0, and both of these go to 0. G prime of c, now we don't know what c is. We're going to find c by solving an equation for x. So I'm just going to put in g prime of x right now. So that's 2 cosine 2x plus 2, okay? So there's some value of x that makes this true, and that'll be our c value. And pi minus 0 is pi, so times pi. And so this simplifies. I get 2 pi is equal to, and let's factor out a 2. And we already have a pi factored out, so we'll bring that over, and that's going to leave cosine of 2x plus 1. And if we multiply through by 1 over 2 pi, we get 1 equals cosine 2x plus 1. And if we subtract 1 from both sides, cosine of 2x is equal to 0. So the question is, when does this happen? Well, so let's just think about cosine for a minute and think about your unit circle. So the unit circle, when is cosine equal to 0? So cosine is going to be equal to 0 whenever the angle, which in this case is 2x, when that angle is equal to pi over 2. Also, cosine will be equal to 0 when the angle is equal to 3 pi over 2. And so this implies that x is equal to pi over 4, or x is equal to 3 pi over 4. And so these actually should be my c values. But let's see if we can take a minute and put this in perspective in terms of what the graphs look like. All right, so what I've done is I've opened Desmos and I've already entered my function g of x, which is sine 2x plus 2x. So here is the graph of that function. Now remember, we're interested in what's going on the interval from 0 to pi, which is approximately over here somewhere. We will find it exactly in a minute. A little bit bigger picture of what's going on. Okay, all right, so first of all, let's do this. Let's go back and think about what was our average rate of change. And so if you remember, we calculated that and we found actually if we were to do f of b minus f of a over b minus a, the 2 pi's would cancel out and I would just be left with the 2. So the 2 is actually the average rate of change. So let me graph the line y equals 2x. Now we can see that there is an intersection of that line with my original function, and you can see that it is at pi, comma, 2 pi. So this is the secant line. The green line is the secant line. That's the average rate of change. And so we can see here this intersection marks the right bound of the interval that we're interested in. So the question is there a point or points on this function where the slope of the tangent line would be equal to the slope of this secant line? And so if you'll recall, we took the derivative of this function, and that was 2 cosine 2x plus 2. Let's graph it. All right, so here's my question. If the slope of this secant line is 2, and I mean clearly it is, right? 0, we go up 4, we go over 2, 4 divided by 2 is 2, slope is 2. If you look at the derivative, what is the x value where the derivative is equal to 2? Well, okay, so on my interval, you know what, let's throw a line in here at x equals pi just to delineate where my interval ends. Okay, so that red line is the boundary. Anything that goes, I'm interested in what's between the y-axis and this red vertical line. So there are 2 places where the derivative is equal to 2. Here and here. What are those x values? Well, we solved for them. They should be pi over 4 and 3 pi over 4. Well, let's do this. Let's graph x equals pi over 4. And sure enough, it intersects my derivative at x equals 2. And if you look at my original function, my g of x, the red function, at that point, I could construct a tangent line parallel to the secant line. What about the other one? 3 pi over 4? Well, there it is. And again, that is the point where the cosine is equal to 2. And this is the point here where I could construct a tangent line parallel to the secant lines. So our solution, so therefore C is equal to pi over 4, comma 3 pi over 4.